Find the head loss in meters across the hydraulic jump. In this problem, a hydraulic jump occurs in a rectangular channel. The channel width is provided, as well as the initial and final water depths. Bernoulli's equation states the total head equals the pressure head plus the elevation head plus the velocity head. Since open channel flow is not pressurized flow, the pressure head for this problem is 0, and the equation simplifies. The head loss across the hydraulic jump is equal to the initial total head minus the final total head, which can be written out in terms of the initial and final elevation heads and velocity heads. The elevation heads, y1 and y2, are simply the water depths given in the problem statement, d1 and d2. The value of g is a constant, but we don't know the velocities, v1 and v2. Velocity 1 and 2 equal the flow rate divided by the area 1 and 2, respectively, where areas 1 and 2 equal the channel base times the depths 1 and 2, respectively. Since we already know the base width and the depths, we need to solve for the flow rate, Q. An equation which relates the conjugate depths across a hydraulic jump is d2 divided by d1 equals 1/2 times the quantity, the square root of 1 plus 8 times the upstream Froude number squared minus 1. For a rectangular channel, the Froude number equals the velocity divided by the square root of the gravitational acceleration times the depth, where the velocity equals the flow rate divided by the area, and the area equals the base width times the depth. After these substitutions are made, the hydraulic jump equation is effectively one equation and one unknown, and that unknown value is our flow rate, Q. After a few lines of algebra, the flow rate is simply a function of the gravitational acceleration and the given data. Plugging in the values for G, B, D1, and D2, the flow rate computes to 10.50 meters cubed per second. To solve for the upstream and downstream velocities, the flow rate, base width, and depths are substituted in, and we get velocity 1 equals 7 meters per second, and velocity 2 equals 1.75 meters per second. By knowing the velocities, we can return to our equation for head loss across the hydraulic jump. Plug in the values for velocity, plug in the values for acceleration and the depths, and the head loss computes to 0.841 meters. Looking over the possible solutions, the answer is B.